Welcome back. We are looking at polar coordinates and some calculus, area, arc length, and then we'll briefly look at surface area, but we're not going to do a problem on that. So polar coordinates are really cool. Different coordinate systems in general are very cool because thinking about things in terms of rectangular coordinates makes a lot of sense in some situations. However, there are lots of other situations where it's not advantageous to think about things in terms of rectangular coordinates. Say if you're looking at distances for things where you're looking at a particular launch angle or something like that, different coordinate systems are super duper useful. So one of them is polar coordinates, where you look at a radius and a theta instead of an x and a y, which are creating a rectangle. Well, how do you get between rectangular coordinates and polar coordinates? Well, this is how. So if you have a point, if you have a location P, let's call it P right there, and that is in terms of x and y, you can also have that exact same location on your flat plane described by a distance away from the origin, or a radius, and an angle of elevation, this theta. And there are also three-dimensional coordinate systems that utilize this radius and this theta, and also another angle phi, and so that's called spherical coordinates. So there's lots of different coordinate systems. It's a really fun internet rabbit trail to go down if you have time. But how do we relate x, y, r, and theta? Well, we can use our old friends cosine and sine, because cosine is looking at your x-coordinate, right? Your x direction, that's for cosine of theta, that's what's going to be your output, but you need to also scale it up because cosine of theta just purely by itself is going to be mapped onto your unit circle, so you need to scale it up by whatever your radius is. So cosine of theta equals x over r, thus if you just multiply by r on both sides, you have x equals r cosine theta. Very similarly, we have sine of theta is going to output a y-coordinate on our unit circle, but we need to scale that up in order to get y by itself with the radius that we're looking at, so y equals r sine theta. Now, this shape is also giving us a triangle, right? A right triangle, which is very nice because then we can use our old friend r squared equals x squared plus y squared, which is a disguised version of a squared plus b squared equals c squared. And we can also think about tangent theta as as y over x, or the slope. So tangent of theta is going to give us the slope of our line that is going from that angle of elevation, that theta that we're looking at. This way, theta. So if you're trying to convert between rectangular and polar coordinates, you just need to plug in your stuff and then solve for what you don't know. Normalize that a little bit. Given a point P in Cartesian coordinates and polar coordinates, you can use these formulas, either direction, either going from rectangular to polar, or from polar to rectangular. Both ways work because we have equations. But this is just an algebra exercise, remembering your trig and being responsible. So how are we going to convert this rectangular coordinates into polar coordinates? Well, we need our radius, and that's going to be root -8 squared plus -8 squared, and that's convenient. I'm also going to do a quick sketch of where that is. It's in quadrant 3. So that gives us 8 root 2, and then our theta is going to be arctan of this this positive 1 slope that we have, right? Or our -8 over 8, -8. And so when is that going to happen? Well, it's going to happen at pi over 4, but that's not the quadrant we want. So this is happening for this at 5 pi over 4, down here, 5 pi over 4. All right. And then converting these polar coordinates into rectangular coordinates, how do we do that? Well, x equals r cosine theta. So x is 4 cosine of 2 pi over 3. 2 pi over 3 is here, so that's cosine is -1/2, so we have -2 is our x value, and y is r sine theta, which is 4 sine 2 pi over 3, and that's what? Positive 4 times root 3 over 2, so 2 root 3. And let's look at this example to see if we did that correctly. So we plug these in, and this is what we have, 3.464, and let's just check, is that, what was it, 2 root 3? Absolutely, we did it. Cool, cool. We'll look at this again in a moment. So when we're looking at coordinates, we also have curves. We can plot coordinates, plot points. That's like a very reliable way of plotting curves into any coordinate system. That's what you used to do before you knew how to graph stuff just from the parent functions in our rectangular coordinates. And so that's going to be your main course of action for figuring out things in the polar coordinates now. But we are also going to have some like general forms that we're going to look at in a table in a little bit. But in order to plot your points, you got to make a table with 2 columns, theta and r, because those are your inputs. Create a list of values, so just choose some thetas. And choose responsibly for things that are actually going to be useful. Calculate your r's, so plug those thetas into your function, and then you will be able to get outputs for r's, plot those ordered pairs, connect them, and look for a pattern. So try this one out. Make a graph for r equals 4 plus 4 cosine theta. And think about what is happening here. We have 4 plus 4 times this value, which is going to be between -1 and +1. So we're going to end up with our maximum r is going to be 4 plus 4, and our minimum r is going to be 4 minus 4. So we're going to have radii from 0 to 8. So think about what that's going to be. Try to plot some points, and then we will check in a bit. What we're coming up with is, as we conjectured, we are going to go from radius 1 to radius 8. And Desmos does polar coordinates if you just flip the grid there. And then you can do inputs with r's and thetas, and it will automatically understand that that is polar, so that's pretty cool. But when you plot your points, you're not able to plug in like r's and thetas directly. You need to do this format that we have up here. Okay, so this is going from here, where if we plug in 0 for theta, that means that we're going to end up with cosine of 0, which is 1. Oh, so we're actually starting here with 4 plus 4 is 8. And then as you move along, as you chug along with your different thetas, you're going to get these values because your cosine is decreasing. And then you're going to get up to here where we have 0 as our output because we have 4 minus 4 because we're looking at theta is pi and cosine of pi is -1. And then we will increase our radii again. This shape is called a cardioid. The cardioid is one of our, I guess, parent functions for polar coordinates. We have others that we will look at later. Just plotting some points. I chose some points that I know the values for my cosine, and then you just plot those points, and then you connect them and see the pattern. So that's the general idea. Plug in thetas that you know, and also if you don't have the unit circle in your brain, then I highly recommend that you get that in your brain. To write this equation, r equals secant theta times tangent theta into rectangular coordinates, and then figure out what kind of graph that is.
let's try to figure out how we can rewrite this in things that we know. So we know like r cosine theta is x. We know tangent theta is y over x. So maybe we can take this secant theta, multiply by cosine on both sides, so that we end up with r cosine theta equals secant theta tangent theta times cosine theta. Cosine and secant are reciprocals, so those cancel to 1. We end up with r cosine theta equals tangent theta. Now we can substitute. R cosine theta is x, tangent theta is y over x, so we end up with y equals x squared, which is a parabola. Right? That's a parabola. So it's pretty cool. We can describe parent functions that we have in rectangular coordinates using polar coordinates. That's pretty sweet. And that makes sense, right? That we can go between the two because we just have these conversion formulas that connect the concepts using what we understand of trig and what we understand of triangles. Math is so cool. So, speaking of parent functions, our good old friend the line, lines with slope of tangent k are going to be able to be described as just theta equals that angle, which is pretty cool. So that's lines. We can have circles, and there's different kinds of circles, because we can also just have like a radius equals like 1, and that's going to give us our unit circle. But if we have circles that are not centered at our origin, then we can describe them with this a cosine theta plus b sine theta, and that's going to give us our new center for where that's going to be. We can see spirals, and spirals are looking at where our radius is happening at some constant value plus b theta something. The parent function for that we're going to look at a little bit later is r equals theta, and this is called the Archimedean spiral. I don't know how to spell Archimedean. I have to use spell check later on, so you'll see how to spell that, but that's where your radius exactly equals your theta. And then, as alluded to before, we have cardioids, and they're named cardioids because they look kind of like a heart. Not an anatomically correct heart, but, you know, the hearts that we all know how to... That's a really bad heart. Like the hearts that we draw when you're just using a writing implement. I'm going to erase this bad heart. But we have cardioids, and those depend on cosines and sines. Depending on if you have a cosine or a sine, is going to determine which axis you have symmetry with respect to, because of how those trig functions work out. A Limassan is a special kind of cardioid where you have a little loop happening instead of just going to a point and then going away. For the Limassan, it passes through. And again, we have different symmetry depending on what you're using, your cosine or your sine. And then we have roses. Roses are actually kind of weird because the number of petals is strange. It's not like really, it's not readily apparent, but if you think about it, it does make sense. So if you have your theta inside your sine or your cosine, and then you multiply it by a b, and that b, depending on if it's an even or an odd integer, you'll have different numbers of petals. And so with even integers that you're multiplying by your theta, that's gonna give you twice as many petals as you have in your number. So here you see we have 3 sine 2 theta. So we're going to end up with 4 petals because we have an even integer multiplied by our theta. And so our number of petals is double the number that we have in there. And if you think about that, that does make sense because you're going effectively like doubling, using the symmetry of your unit circle to your advantage in determining how many petals you get. And then if you have an odd number of petals, and you have exactly that number of petals. If you have a b is odd, so what you're multiplying by in here, is odd, then you're going to end up with that number of petals. This is the Archimedean spiral. And once again, that's just a special case of our spiral where r equals theta. And it's just really nice. It comes up in some stuff. So, let's talk about symmetry now. So there are different kinds of symmetry. So remember how when we were looking at symmetry in rectangular coordinates, we had symmetry with respect to the x-axis, symmetry with respect to the y-axis, and then we had like this rotational symmetry where you can plug in opposites and get out opposites. So similarly with polar, we have symmetry with respect to the polar axis, which is our horizontal axis, because this is our r. So this is our polar axis. And then we have symmetry with respect to the pole. The pole is our origin. And symmetry with respect to our vertical axis, which isn't named in the sense that we don't call it our like radius. This is like the radii are all determined by this first one, the horizontal polar axis. So those are your different kinds of symmetries. It's pretty nice. And in general, remember how we use symmetry to our advantage when we're evaluating integrals? We can do the same thing in polar coordinates. So we need to determine our symmetry of our graph, given by this equation where we have 2 cosine of 3 theta, and make a graph. We're probably going to use Desmos for the graph, just because I'm not great at drawing curves. But let's think about what this is going to be. Well, this looks like the rows. We have b equals 3, which is odd. So then we know that that means that we have 3 petals. We have 2 times, so we have a equals 2. So that means that we're going to get out to, like our maximum r is going to be 2. And because we're looking at cosine, cosine is going to give us symmetry with respect to the horizontal axis, or the polar axis. So let's think about what this is going to look like. I told you that I was going to use Desmos, but you know, we should also plug in some points. So if we say like theta equals 0, what's going to happen? We end up with cosine of 0, which is 1 times 2, so that gives us 2. If we let's just choose another theta. Let's choose theta is pi. So what happens at pi? And this is not precise enough to be able to sketch a graph, but we have, if theta equals pi, then we end up with cosine of 3 pi, and 3 pi is -1, so we end up with 2 times, cosine of 3 pi. 1 pi, 2 pi, 3 pi. Cosine of that is -1, so we end up with -2. Something went awry. Hang on. Right. When we have negative as our radius, that doesn't work. So that's cool. Didn't know. Okay. What if we had, well, what if we had cosine of pi over 2? So then we end up with 2 times cosine of 3 pi over 2. 3 pi over 2, that gives us 0. So pi over 2, we get 0. So we're going to end up with a rows that looks like this. And then we're actually going to go down here, and then up here, and then over there, and then like that. I'm going to show you the Desmos one, though, because it's way better.
So if you plug in your r here, this is what your graph is going to look like. And the 2 pi over 3, that makes sense that that's going to be out here at our radius 2, because if you plug in 2 pi over 3 into this for theta, then you end up with 2 pi, and 2 pi is going to give us positive 1, so 2 times 1 is 2, and so that's right there, and that's pretty great. Calculus, and so we're going to do some calculus. We're not in coordinates, rectangular coordinates anymore, so when we're integrating, like our area under our curve, we can't use rectangles anymore, which is a bummer. But that's okay, because we are in polar coordinates, and so instead of looking at rectangles, we can look at like slices of circles, so that we can add up these little like parts, and that's going to come from our understanding of areas of circles, or sectors. And also arc length is going to work as well, because we can just look at our arc lengths, which are something that we can break down in terms of our polar coordinates. So even though we're not in rectangular coordinates anymore, so we can't use these rectangles, we can use areas of sectors. So let's get to it. Our area of a sector. I feel like that's something that, you know, it's just maybe you picked up along the way, maybe you didn't, but our area of a circle is pi r squared, right? So if we're looking at the area of just a particular sector of our circle, that means that we're looking at some theta amount determined not by our entire circle, but just by a particular theta of that. So our area of our sector is going to be the same r squared, but we are actually multiplying by theta over 2 to get our area of our sector. Think about why that makes sense. It makes sense because your theta over 2 pi is like the fraction of the entire circle that you're looking at, which is 2 pi. And so if you're just looking at a particular theta, then you're taking this area of your whole circle, which is pi r squared, and multiplying it by theta over 2 pi. And then those pi's cancel out, and you're left with area of your sector is theta over 2 times r squared. Find the area of a region bounded by your polar curve. Well, you've got to assume that you have continuous and non-negative f output, an f function, on an interval from alpha to beta. And we're also looking in general at the difference of these is between 0 and 2 pi, so that we don't like repeat our areas and then we end up with something infinite, because we're only looking at like one period of our polar curve. So the area of our region is bounded by our graph r equals f of theta between radial lines, theta equals alpha and theta equals beta. So that's looking at like a line alpha to a line beta, where this is what we're looking at integrating, something in here. So our area is 1/2, right? But from our area of our sector is theta over 2 times r squared. And our r is given by our function of theta, and then we're squaring that. But we got to integrate that because we got to add up an infinite number of these guys. So how are we going to determine the area of our inner loop of this, which is a Limassan? First, we got to figure out what our alpha and beta are, and then we can integrate. So try that out by plugging in some numbers. So make our table, plug in some thetas, and see where we can get r equal to be 0. So, well, pi over 3 is going to give us positive 4, so that's not going to work. But that's pretty close, right? Because then we ended up with this is going to be, or this whole thing was 1/2 times 4. So maybe 2 pi over 3? Is that going to give us 0? It is, because that gives us a negative 1/2, so then we end up with a 0 here. When is our next 0 going to come about? Our next 0 is coming up, I think, at the next pi thirds. We have the 2 pi over 3 and then the 4 pi over 3, so that gives us a 0 as well. So this is our alpha and this is our beta. So we're integrating from 2 pi over 3 to 4 pi over 3 of 1/2 times what is our r? We're looking at 2 plus 4 cosine theta, and we're squaring that and we're integrating with respect to theta. And so what ends up happening here, we got to expand, so we get, what is this, 1/2 integral 2 pi over 3 to 4 pi over 3 of 4 plus 16 cosine theta plus 16 cosine squared theta d theta. Maybe we need to power reduce on this cosine squared so that we can just deal with less of this. So we can have what is this? Integral of 2 pi over 3 to 4 pi over 3. I'm going to distribute this 1/2 everywhere, so we end up with 2 plus 8 cosine theta plus 8 times, and that's a 1 plus cosine 2 theta, right? Because cosine, cosine, sine, 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 and then do some substitutions, and then we end up with that. Identity, d theta. And does that help us? Oh no, wait, this isn't an 8, this is a 4, because we got to divide by a 2. That's right, this is cosine squared theta equals 1 plus cosine 2 theta over 2. And then we can integrate, right? And so we end up with 6 theta from this 2 and this 4, plus 8 sine theta from here, plus 2 sine of 2 theta, going from 2 pi over 3 to 4 pi over 3. And when do we end up with? It's going to be some algebra happens, and then we end up with a 4 pi minus 6 root 3. So that is our area of our inner loop of this, which is a Limassan. I guess we can sketch this out. We got 6, and then we go like this. That's really terrible. But this line is given by 2 pi over 3, and this line is given by 4 pi over 3. Alright, let's try another example. So, figure out the area that lies inside this curve, but then outside r equals 2, which is a circle. So, for area between curves, it's just going to be pretty much the same thing that we did before with our rectangular coordinates, where you take just your top minus your bottom, but in this case with our radii, we're looking at our outer radius minus our inner radius. So we're looking at our same bounding alpha and beta theta angles, and then we have this 1/2, and then we have the difference between our
r squareds for the outside minus the r squared of your inside curve, and you're integrating with respect to theta. So try to determine which is the outside, which one is the inside, which is given pretty much in the problem. This is our r outer, and this is our r inner. And then what are our alpha and beta, and then try to go from there. These two are going to intersect pretty much. Could just set these two equal. So we have 2 equals 3 plus 2 sine theta. And so then negative 1/2 equals sine theta when theta equals what? Sine is our y, so sine is negative 1/2 at 7 pi over 6. And also at 11 pi over 6, which you could write as negative pi over 6, but just in terms of keeping everything between 0 and 2 pi for our bounds, we like these better. And so we get our area is 1/2 times the integral of 7 pi over 6 to 11 pi over 6. And then what do we have? We have 3 plus 2 sine theta squared minus 2 squared d theta. So try to crunch that out, use some trig things, and see what you get. So from there, we just get some sine squareds, right? So we have, this is 7 pi over 6 to 11 pi over 6. And then we got 9 plus 12 sine theta plus 4 sine squared theta. And I gotta move over. And then we have this minus 4 d theta. So then we end up with, oh, and there's a 1/2 in the front. Can't forget that 1/2. So we end up with 1/2 from 7 pi over 6 to 11 pi over 6 of 5 minus 12 sine theta plus 4 sine squared theta, but sine squared theta is going to be cosine. That's a cosine identity, right? Where we can have our power reduction, and it's 1 minus cosine of 2 theta over 2. And so we end up with, let's see, 4 times this, which is 4 times that. And so we have 2 minus 2 cosine 2 theta, d theta. And that's pretty straightforward to integrate. And so we end up with 1/2, 7 thetas plus, cosine, minus 12 cosine thetas, minus, because we have the negative cosine, so then it's a negative sine, and there's a 2 of those, sine 2 theta over 2, and so those cancel, and we're going from 7 pi over 6 to 11 pi over 6. You chug through some of that arithmetic and you end up with 11 root 3 over 2 plus 14 pi over 3. And that's your area between your two curves
r equals 3 plus 2 sine theta, and r equals 2. Alright, so let's think about arc length. So when we're looking at arc length in rectangular coordinates, using parametrically defined functions, this is what we have, right? We have a to b, our integral from a to b on the square root of our differentials, our derivatives with respect to t, which is our parameter. And so let's just say that t equals theta. So then we can say this arc length, and we're changing our bounds in terms of theta, so we have alpha to beta of the square root of dx d theta squared plus dy d theta squared d theta. And then if we go from here, we can rewrite our dx d theta in terms of a function f of theta. So our derivative with respect to x, derivative of x with respect to theta is f prime of theta times cosine of theta minus f of theta times sine of theta because of the product rule, and dy dx d theta is going to be f prime of theta times sine theta plus, because of the product rule, we're taking our derivative of sine, and so then we don't change our sign, sine. So we have f of theta times cosine of theta. And so we plug those in here, and then we'll do some algebra. So let's see. Alpha to beta, our integral from alpha to beta of root, and then we have f prime of theta cosine theta minus f of theta sine theta, and we're squaring all of that, plus, and then this is a big parentheses for this, f prime of theta sine theta plus f of theta cosine theta squared d theta. Okay, so that was just this substitution of these two in for x dx d theta and dy d theta. And now, well, we need to multiply out and then combine some like terms. So what do we end up with? Integral from alpha to beta of our square root, and so our f prime cosine minus f prime sine is going to give us f prime theta cosine theta squared minus 2 f prime theta cosine theta f of theta sine thetas plus f of theta times sine of theta squared, and that's just this part. And then for this part, we end up with plus f prime of theta sine theta squared plus 2 f prime of theta sine of theta f of theta cosine theta, and then plus f of theta cosine of theta squared. And then we're doing all of that with respect to, and this is all inside our radical d theta. Okay, so now it's time to get excited because we're going to have a lot of cancellations happening. So this this negative 2 and positive 2 of the same thing, those are going to cancel. So what's highlighted in yellow cancels out with itself. F prime squared with the sine squared, and this f prime squared times this cosine squared. That's going to give us a Pythagorean identity with the cosine and the sine. And then this f of theta times sine theta, and this f of theta times cosine of theta squared. Those are also going to give us a Pythagorean identity. So what are in blue and what are in green are going to simplify out to just f prime squared plus f squared. So let me sneak over here. So the blue and the green end up giving us our integral from alpha to beta. Move over here. Of square root of f prime of theta squared plus f of theta squared d theta. And, well, that's, because f of theta is r, f prime of theta is dr d theta, so we can also rewrite this as our integral from alpha to beta, and this is our arc length, remember, of root r squared plus dr d theta squared d theta. Whew, that was fun. So, formalized a little bit, we got our arc length equals this. So, if we're looking at the length of r equals theta, which is our Archimedean spiral, from 0 to theta, what do? We go from 0 to 1 on theta. And then we have the square root of r, which is theta, squared, plus, and then dr d theta is 1, so 1 squared d theta. And so what happens there? I think we need to do a trig sub. So we have root of something squared plus 1 squared, which is just 1. Alright, so I'm going to just do that. But let's say, I think the trig sub we need is using tangent. So theta equals tangent of x. And so then our derivative is going to be secant squared of x dx. And so what's happening here? Well, we're going to end up with root theta squared plus 1 is going to give us root tangent squared plus 1, tangent of x plus 1. And what's that? Well, tangent squared plus 1 is secant squared, right? Because cosine squared x plus sine squared x equals 1. So if you divide everything out by cosine, divide by cosine squared, and you end up with tangent squared x plus 1 equals secant squared x. So this is root secant squared x. Root secant is just the absolute value of secant. And then what we're looking at is actually going to be what? Oh, we need to change our bounds too. So when theta equals 0, then x is 0. And when tangent equals 1, then x is pi fourths. So our bounds are from 0 to pi over 4 of secant secant x, which is this, times d theta, which is secant squared of x. And then that's secant cubed. Let's see. So we're going to end up with secant cubed.
How do we integrate secant cubed? Do we need to put that back into terms of tangent, where we have secant times tangent squared plus 1? Does that help us? Now I need to think about this. Should we do integration by parts for the secant cubed? Alright, so we got u is secant, du, dv is secant squared. So then v is tangent, and du is secant x tangent x. So then we have this equals our integral uv, so secant tangent, minus the integral of v du. v du is secant x tangent squared x dx from 0 to pi over 4, and that's from 0 to pi over 4 as well. And this tangent squared x is going to be secant squared x minus 1. So we can do that substitution. So you end up with secant x tangent x minus the integral of secant x times secant squared x minus 1 dx, and that's from 0 to pi over 4. And so that's secant x tangent x minus integral from 0 to pi over 4 of secant, not sine, secant cubed x minus secant x dx, and that's, we can put a dx there, integral there, 0 to pi over 4. And that's nice because that means that this equals this, so we can simplify, maybe I'll zoom out so we can see everything. And so that means that we have 2 times the integral from 0 to pi over 4 equals secant of secant cubed x equals secant x tangent x from 0 to pi over 4 minus the integral of secant x dx from 0 to pi over 4. And so that's nice. Secant is like natural log of secant plus tangent. So we have integral of 0 from 0 to pi over 4 of secant cubed x is 1/2 times secant x tangent x 0 to pi over 4 minus natural log absolute value secant x plus tangent x from 0 to pi over 4, and then we can evaluate. Oh my goodness. So what do we end up with? I think we end up with something along the lines of (1/2) times root 2 plus natural log of 1 plus root 2. For our arc length. So the arc length of r equals theta from theta between 0 and 1 is that. Wow. So many things. We talked about integration by parts, and that was lovely. Alright, last thing. Surface area. We're not going to do an example of this, we're just going to think about it. The surface area is going to be 2 pi y, or 2 pi x, depending on which direction you're rotating around, with respect to the surface, the differential. So, and that's going to be your arc length, which we just talked about extensively. So surface area works the exact same way that it did before, where you're multiplying your arc length times 2 pi times the radius times the height of your cylinders. All right, that about does it. Sorry this one's so long. Bye.